Hello class. Today we're going to discuss normalization in chapter 6. So normalization in a nutshell is the process by which we separate and organize data into relations to allow for the most suitable balance between the speed of retrieval of data and the effort needed to manage it. For a quick illustration of why we normalize data, please consider figure 6.1 in the text on page 192. This figure shows a table of data such as you might find in a spreadsheet organization of information. For the moment, consider that a business is using this format to store their project and employee information, and that this figure represents either a spreadsheet or a single table database. Indeed, it was not uncommon for businesses to use books or spreadsheets in just such a way. Now take a look at the employee's name column. Do you notice that the second person, John G. News, is listed under two projects, both Evergreen and Starflight. Now, if Mr. News's title was to be changed from database designer to database administrator, it would be possible to look line by line through this spreadsheet and find each instance of his name and change his entry in the job class column. But what if you missed one? What if the hours in this table were updated in only one location for a particular person? Would Mr. News get paid accurately? This type of problem is with the integrity of the data. It's possible to change data in one location and not another. Similar issues arise if the company decides to change the title of all electrical engineers to another name, or if you tried to sort this table by any other means than the way it is currently arranged. While this table might suffice for a small business with limited projects if human users were careful in how they reviewed it and used it, normalizing this out into multiple tables in a relational database would improve more data integrity and give this data greater utility and greater ease of use. So normalization is an iterative process. It consists of multiple stages. The first normal form, which is written as 1 capital N capital F, in this form, the first step is to convert it by filling in all of the empty cells in the table. See the columns for project name and project number so that no cells are left empty or left null. And then we need to identify a key for the table because all tables in our databases need to have keys. We cannot use project number because it's repeated and so it's not unique. And because the employees are listed each time they are in a project, there are multiple employee entries, so there's also multiple times that the employee number shows up. However, we can use a composite key of the project number and the employee number used together, and in that case there's no combination of this that's not unique. So identifying keys also eliminates a dependency in that the rest of the data in the table for a particular entry can be uniquely identified by a combination of project number and employee number so that data is dependent on the key. Another dependency is that employee name, job class, and charge hours are dependent on the employee number. Project names are dependent on project numbers and charge hours are dependent on job class. So now that we've filled in the table, we can move on to the second normal form. The first step in accomplishing the second normal form, also written 2NF, is to create new tables to handle the dependencies we found in the first normal form. Project name, for instance, is dependent on project number. So we make a new table, perhaps call it project, and in it store the project number and the project name. In the original table, we'll keep project number, but we will remove project name. Now the new table project has a primary key of a project number, and in the original table that column serves as a foreign key, creating a relationship between these two tables. We will do the same for all the dependent relationships in the original table, moving those dependent attributes to their new tables and leaving behind foreign keys. And that will bring us to third normal form. To reach third normal form, we will look for and eliminate any transitive dependencies. In this case, the column charge hour has a transitive dependency on job class. To normalize this, we will make a new table called job, and we will populate it with the attributes job class and charge hour. We'll leave behind a copy of job class to become a foreign key in the originating table, and in the new table we assign job class as a primary key. Eliminating the attribute charge hour from the originating table completes this step, and if there were more transitive dependencies, we would work on eliminating them as well. For our sample data, that was the only transitive dependency. So the final level, also known as fourth normal form, or 4NF, is not something that you'll have to worry about much in the real world. If you have normalized your data through the iterative process using the steps above, then you will be done at 3NF, where most databases exist. They're in use in the real world. In rare cases, you perhaps inherit a poorly designed database system, and it may have multi-valued dependencies. If so, eliminating these is done in a similar manner by moving attributes into new tables. At this point of the process of normalization, you should be able to see multiple tables and relationships similar to the results you achieved in designing database diagrams when you were building a system from scratch for yourself, illustrating entities and their attributes and relationships. Individual entities such as employee or class have now been separated out and exist as independent tables. Sometimes new entities may need to be created in instances where you have complicated many-to-many relationships or end-to-end relationships. A good illustration of this is found in figure 6.15 or 6.15 in the book. So now that we have learned how to normalize our data, let's consider when it is appropriate to not normalize or to denormalize data. Denormalization is when we separate out, or normalization is when we separate out every possible entity and develop a database and we create something that a database management system can very effectively manage. To get data out for an end user, we send queries to the database management system, and it compiles the results by going to the appropriate tables and compiling our answer. Each table it accesses, though, increases the amount of work it must do to answer the query. In some cases, there may be ways to denormalize, that is, to put dependent entities back into other tables to increase the speed of performance by sacrificing a bit of the normalization. Consider that a city in an address is dependent on the zip code, so the field city is dependent on or the attribute city is dependent on the attribute zip code. To perfectly normalize a data set that has these and contains street addresses, we would need to move to a new table, create a table called zip code and include zip code and city in it, and use zip code as a foreign key back in the address table pointing to this new table. If we do this, however, when someone queries to get an address, both tables have to be accessed. It is unlikely that we would benefit from separating out zip codes into their own table. Zip codes don't change very often, and the zip code of a city or an area that it's dependent on doesn't change very often, so we're unlikely to run into problems with data integrity where a city was changed for a particular zip code and we had multiple entries in our address table. So, and since addresses are typically used with zip and city all the time, we find it acceptable to keep zip code and city in the same table with the rest of the address. Just like in Chapter 4 when we talked about sometimes storing derived data to increase performance, denormalization is a thoughtful way of having a less perfectly normalized data in order to decrease the workload the database management system performs and thus increase the performance speed. Thank you very much for watching.